So last year, on the 4th of July, experiments at the Large Hadron Collider discovered the Higgs Boson. It was a historical day. There's no doubt that from now on, the 4th of July will be remembered not as a day of the Declaration of Independence, but as a day of the discovery of the Higgs Boson. Well, at least here at CERN. But for me, the biggest surprise of that day was that there was no big surprise. In the eye of a theoretical physicist, the Higgs boson is a clever explanation of how some elementary particles gain mass. But it seems a fairly unsatisfactory and incomplete solution. Too many questions are left unanswered. The Higgs boson does not share the beauty, the symmetry, the elegance of the rest of the elementary particle world. For this reason, the majority of theoretical physicists believed that the Higgs boson could not be the full story. We were expecting new particles and new phenomena accompanying the Higgs boson. Instead, so far, the measurements coming from the LHC show no signs of new particles or unexpected phenomena. Of course, the verdict is not definitive. In 2015, the LHC will almost double the energy of the colliding protons. And these more powerful collisions will allow us to explore further the particle world. And we will certainly learn much more. But for the moment, since we have found no evidence for new phenomena, let us suppose that the particles that we know today, including the Higgs boson, are the only elementary particles in nature, even at energies much larger than what we have explored so far. And let's see where this hypothesis is going to lead us. We will find a surprising and intriguing result about our universe. And to explain my point, let me first tell you what the Higgs is about. And to do so, we have to go back to 1/10 of a billionth of a second after the Big Bang. And according to the Higgs theory, at that instant, a dramatic event took place in the universe. Space-time underwent a phase transition. It was something very similar to the phase transition that occurs when water turns into ice below 0 degrees. But in our case, the phase transition is not a change in the way the molecules are arranged inside the material, but is about a change of the very fabric of space-time. During this phase transition, empty space became filled with a substance that we now call Higgs field. And this substance may seem invisible to us, but it has a physical reality. It surrounds us all the time, just like the air we breathe in this room. And some elementary particles interact with this substance, gaining energy in the process. And this intrinsic energy is what we call the mass of a particle. And by discovering the Higgs boson, the LHC has conclusively proved that this substance is real, because it is the stuff the Higgs bosons are made of. And this, in a nutshell, is the essence of the Higgs story. But this story is far more interesting than that. By studying the Higgs theory, theoretical physicists discovered, not through an experiment, but with the power of mathematics, that the Higgs field does not necessarily exist only in the form that we observe today. Just like matter can exist as liquid or solid, so the Higgs field, the substance that fills all space-time, could exist in two states. Besides the known Higgs state, there could be a second state in which the Higgs field is billion and billion times denser than what we observe today. And the mere existence of another state of the Higgs field poses a potential problem. This is because, according to the laws of quantum mechanics, it is possible to have transitions between two states, even in the presence of an energy barrier separating the two states. And the phenomenon is called, quite appropriately, quantum tunneling. Because of quantum tunneling, I could disappear from this room and reappear in the next room. practically penetrating the wall. But don't expect me to actually perform the trick in front of your eyes, because the probability for me to penetrate the wall is ridiculously small. You'd have to wait a really long time before it happens. But believe me, quantum tunneling is a real phenomenon, and it has been observed in many systems. For instance, the tunnel diode, a component used in electronics, works thanks to the wonders of quantum tunneling. But let's go back to the Higgs field. If the ultra-dense Higgs state existed, then, because of quantum tunneling, a bubble of this state could suddenly appear in a certain place of the universe at a certain time. And it is analogous to what happens when you boil water. Bubbles of vapor form inside the water, then they expand, turning the liquid into gas. In the same way, a bubble of the ultra-dense Higgs state could come into existence because of quantum tunneling. The bubble would then expand at the speed of light, invading all space and turning the Higgs field from the familiar state into a new state. Is this a problem? Yes, it's a big problem. We may not realize it in ordinary life, but the intensity of the Higgs field is critical for the structure of matter. If the Higgs field were only a few times more intense, we would see atoms shrinking, neutrons decaying inside atomic nuclei, nuclei disintegrating, and hydrogen would be the only possible chemical element in the universe. And the Higgs field in the ultra-dense Higgs state is not just a few times more intense than today, but billions of times. And if space-time were filled by this Higgs state, all atomic matter would collapse. No molecular structures would be possible, no life. So I wonder, is it possible that in the future the Higgs field will undergo a phase transition and through quantum tunneling will be transformed into this nasty ultra-dense state? In other words, I ask myself, what is the fate of the Higgs field in our universe? And the crucial ingredient necessary to answer this question is the Higgs boson mass. And experiments at the LHC found that the mass of the Higgs boson is about 126 GeV. This is tiny when expressed in familiar units because it's equal to something like 10 to the minus 22 grams. But it is large in particle physics units because it is equal to the weight of an entire molecule of a DNA constituent. So armed with this information from the LHC, together with some colleagues here at CERN, we computed the probability that our universe could quantum tunnel into the ultra-dense Higgs state. And we found a very intriguing result. Our calculation showed that the measured value of the Higgs boson mass is very special. It has just the right value to keep the universe hanging in an unstable situation. The Higgs field is in a wobbly configuration that has lasted so far, but that will eventually collapse. So, according to these calculations, we are like campers who accidentally set their tent at the edge of a cliff. And eventually, the Higgs field will undergo a phase transition and matter will collapse into itself. So, is this how humanity is going to disappear? I don't think so. Our calculation shows that quantum tunneling of the Higgs field is not likely to occur in the next 10 to the 100 years. And this is a very long time. It's even longer than the time it takes for Italy to form a stable government. Even so, we will be long gone by then. In about 5 billion years, our sun will become a red giant, as large as the Earth's orbit, and our Earth will be kaput. And in 1,000 billion years, if dark energy keeps on fueling space expansion at the present rate, you will not even be able to see as far as your toes, because everything around you expands at a rate faster than the speed of light. So it is really unlikely that we will be around to see the Higgs field collapse. But the reason why I am interested in the transition of the Higgs field is because I want to address the question, why is the Higgs boson mass so special? Why is it just right to keep the universe at the edge of a phase transition? Theoretical physicists always ask why questions. More than how a phenomenon works, theoretical physicists are always interested in why a phenomenon works in the way it works. We think that these why questions can give us clues about the fundamental principles of nature. And indeed, a possible answer to my question opens up new universes, literally. It has been speculated that our universe is only a bubble in a soapy multiverse made out of a multitude of bubbles. And each bubble is a different universe with different fundamental constants and different physical laws. And in this context, you can only talk about the probability of finding a certain value of the Higgs mass. Then the key to the mystery could lie in the statistical properties of the multiverse. It would be something like what happens with sand dunes on a beach. In principle, you could imagine to find sand dunes of any slope angle in a beach. And yet, the slope angles of sand dunes are typically around 30-35 degrees. And the reason is simple. Because wind builds up the sand, gravity makes it fall. As a result, the vast majority of sand dunes have slope angles around the critical value, near to collapse. And something similar could happen for the Higgs boson mass in the multiverse. In the majority of bubble universes, the Higgs mass could be around the critical value, near to a cosmic collapse of the Higgs field, because of two competing effects, just as in the case of sand. My story does not have an end, because we still don't know the end of the story. This is science in progress. And to solve the mystery, we need more data. And hopefully, the LHC will soon add new clues to this story. Just one number, the Higgs boson mass. And yet, out of this number, we learn so much. I started from a hypothesis that the known particles are all there is in the universe, even beyond the domain explored so far. From this, we discovered that the Higgs field that permeates space-time may be standing on a knife edge, ready for cosmic collapse. And we discovered that this may be a hint that our universe is only a grain of sand in a giant beach, the multiverse. But I don't know if my hypothesis is right. That's how physics works. A single measurement can put us on the road to a new understanding of the universe, or it can send us down a blind alley. But whichever it turns out to be, there's one thing I'm sure of. The journey will be full of surprises. Thank you.